So, hello everyone. Today we are going to see limit theorems. Before that, we need to understand what is tails of sequence. So I've written down the definition over here. Sequence X, and M tail of sequence X is X of M. So it is denoted by X of M, M in subscript. It is the M tail of a sequence X. So what is it? It is actually the set of X of M subscript M plus N such that N belongs to natural. So it is nothing but the set of X of M plus 1, then X of M plus 2, then X of M plus 3, and so on. So it is basically a part of X, the sequence. Now we go into our first theorem, which is theorem 0. So it states that X of M converges if and only if X converges. So this is an if and only if statement, and you need to show both sides of the statement to prove this thing. So I leave it to you. I leave this theorem to you as a problem. It's very easy to prove. Just try it out. Then we have got another theorem which I've boxed out over here, which is uniqueness of limit. What I want is try out this also as a problem. So it states that a sequence in R can have at most one limit. You can try out this theorem as another problem. You will be only needing the basic idea of limit of a sequence to prove this thing. So try out these two things and let's move on. Now, the important stuff, limit theorems. Before that, again, you need to understand one more thing, that is boundedness. So what is boundedness? In most of the times we find the term boundedness in inequalities. So it states that sequence X of R is said to be bounded if there exists a positive M belonging to R such that the mod value of X of N is less than equals to M for all N belonging to natural. Now we have got a theorem on it. So theorem 1, it states that a convergent sequence is always bounded. And how will you prove it? For the proof, we are only going to use the idea of limit of a sequence. Since we know that the sequence converges, we can write that mod of xn minus lambda is less than epsilon for all n greater than equals to some k of epsilon. Over here the lambda is our convergence point. So we let this thing as our first equation. But we need to show that x is bounded. How will you do it? So we need to show that x of n is less than equals to m for all n belonging to natural. We do it like this. We can write mod of xn as mod of xn minus lambda plus lambda. Then we can apply triangle inequality to write that mod of xn is less than or equals to xn minus lambda, the mod value of this thing, plus the mod value of lambda, the basic triangle inequality. Now we can replace the mod of xn minus lambda as epsilon, and this condition is true as long as n is greater than or equals to k of epsilon. So we found an upper bound for x if n is greater than or equals to k of epsilon. But what about the preceding terms? We can simply tackle it by letting a variable m, which is equal to supremum. So supremum function gives us the maximum value in a given set. Supremum of x, mod value of x of 1, then x of 2, then it goes on till x mod value of x of k minus 1, and finally epsilon minus epsilon plus mod of lambda. Sorry about that. So since this is a finite set, we can compare the terms and the supremum function is thus applicable. Remember, the supremum function will give us the maximum value. So if x of 5 is a maximum value, so it will give out x of 5 and then m will be x of 5. that is just an example. So we find that mod of xn is less than equals to m for all n belonging to natural. So we wanted to prove this thing, and as you can see, the proof was very simple. It didn't require us any sophisticated tool. We just needed the idea of limit of sequence. So we are done with this proof, and we will go on to our next theorem, that is theorem 2. So theorem 2 states that if I have got two sequences x and y that converge to x and y respectively, then the additive sequence must converge to x plus y. The sequence subtract x minus y sequence should converge to x minus y, and xy should converge to xy. And if we are given a sequence z where z is a non-zero sequence, then the quotient function will also converge to its quotient convergence point. So proof, I'm only going to show the first one. The rest of the three are all similar and you can try it out on your own. So for the first one, since x and y are convergent sequence, we can write x of n minus x is less than epsilon for all n greater than equal to some k1. Obviously k1 depends upon epsilon. And similarly we can write y of n minus y is less than epsilon for some for all n greater than equals to some k2. Now k1 and k2 are different, but we want to compare these two inequalities together. So what we do is we let k is equals to supremum of k1 and k2. So we can, after doing this, we can actually see that k is greater than equals to k1 and k2. So then the first inequality comes out to be x of n minus x, the mod value of this thing, is less than epsilon for all n greater than k. Can we write this? Obviously we can, because k is itself greater than k1. Similarly, we can do it for the terms in y, and we can write that mod of y of n minus y is less than epsilon for all n greater than is equals to k, which is further greater than or equals to k2. This is possible because k is maximum of k1 and k2. Now we can add up both this inequality and we get that mod of xn minus x plus mod of yn minus y is less than twice epsilon. So we'll let this as our first equation, and remember this inequality is true if n is greater than or equals to k. Now we need to show that the sequence x of n plus y of n converges to x plus y. So from limit of a sequence, we need to show that the mod value of x of n plus y of n minus x plus y, it should be less than epsilon, where epsilon is an arbitrary positive value. So just doing some manipulation, we can write that the mod value of x of n plus y of n minus x plus y is actually less than the mod value of x of n minus x plus y of n minus y. Then applying triangle inequality, we get that it is less than or equals to mod of x of n plus mod of y of n minus y. And further we know that this quantity is less than twice of epsilon for all n greater than equals to k. So we finally write that mod value of x of n plus y of n minus x plus y, this mod value is less than epsilon prime, where epsilon prime is twice of epsilon, and this is true for all n greater than equals to k. So epsilon prime is twice of epsilon, and since epsilon is positive and arbitrary, epsilon prime is also arbitrary and positive, and hence we are done with our proof. So now we are going to look at theorem number 3. It states that if x of n is a sequence that converges and x of n is greater than or equal to 0 for all n belonging to natural, that implies limit x of n tends to infinity is also greater than or equal to 0. So the convergence point should also be greater than 0. So for the proof, we will prove this using contradiction. So we suppose that the limit n tends to infinity x of n equals to lambda and this quantity is less than 0. Then from the definition of limit of a sequence we can write mod of x of n minus lambda is less than epsilon for all n greater than or equals to some k of epsilon. Again using the basic definition of limit of a sequence. Now, if we remove the mod sign and do some manipulation, we get that lambda minus epsilon is greater than x of n, which is less than lambda plus epsilon. So, now lambda is less than 0. We know that lambda is less than 0. Uh, and as we know that lambda is less than 0, so it is obvious that minus lambda is greater than 0. So we can write minus lambda is greater than 0. And since epsilon is positive and arbitrary, we can obviously set epsilon to be minus lambda. If we do so, we get that twice of lambda is less than x of n, which is further less than the 0. But this is a contradiction since x of n is always greater than or equals to 0, and over here we find that x of n is less than 0 for all n greater than or equals to k of epsilon, and when epsilon equals to minus lambda, and this is a contradiction. Hence our assumption was wrong and we need to write that limit n tends to infinity x of n is greater than equals to 0. So now we will use this theorem to prove some other theorems. So we go into theorem number 4, which is actually an extension of theorem number 3. It states that if x of n is a sequence and y of n is a sequence, both converges. So both should converge, and x of n is less than equals to y of n for all n belonging to natural. So that implies the convergence point of x of n is less than the convergence point of y of n. So how will we do that? Once again, for the proof, what we do is we let z of n be a sequence which is defined by y of n minus x of n. So from the basic definition and the given condition, we can say that z of n is greater than or equals to 0 for all n belonging to natural. Then applying theorem number 3, we can write limit n tends to infinity z of n is greater than or equals to 0. Now, z of n is y of n minus x of n, so we can write limit n tends to infinity y of n minus y of n minus x of n is greater than or equals to 0. Now we know that we can break the limit in addition subtraction case. So we break the limit and we get that limit n tends to infinity y of n minus limit n tends to infinity x of n is greater than equals to 0. I think now you can clearly see the coming result. So definitely then y of limit n tends to infinity y of n is greater than or equals to limit n tends to infinity z of n. Again a very simple proof. As I told you, it was just an extension of theorem number 3. Now with a further we can further extend this theorem by adding some more conditions. So another extension of this theorem is if with all the conditions of theorem number 4 we are further given that y of n is less than equal to z of n, and again these two sequences converges for all n belonging to natural. Obviously this condition is true for all n belonging to natural. Then we can write that limit n tends to infinity x of n is less than limit n tends to infinity y of n, and which is again by using theorem number 4 on y of n and z of n, which is we get that it is less than limit n tends to infinity z of n. So again, this is a very effective way of showing some inequalities